It was off. Is it on? Testing? Testing? All right, perfect.
Go ahead.
Awesome. All right. Hello, everyone. For those of you that don't know me, my name is Josh. This is MoonLight. I'm replacing Oliver this week. So if you haven't been to MoonLight before, essentially it's a group of students that get together every Wednesday night at 9 p.m. to talk about our side projects, whether that's a business you're working on or just a fun little game or a tool you're building for yourself, whatever that is, it's a place to come talk about it and get feedback. So the meetings typically split up into two parts. So the first half is just anyone can grab the mic, come up, and rant about their idea for 5 minutes. We can get some feedback from fellow students, can be questions. And then at the end of those, we have a demo. And tonight's demo is actually really exciting. It is J-Gravity. And so this is, I believe, their first presentation, so we're really excited for that. So to kick off, if anyone wants to come up and talk about their idea, it's just a great way to get feedback and show other students what you're working on. Anyone want to go? Anyone? Do you have no side projects? Come on. If you have an idea, just come and talk about it. We have people that just ramble on about something they want to build.
Hi, my name's Joe. I just started here at 42 Sunday. Came all the way here not knowing that I was going to get a dorm. And it is to the beautiful work of the RAs who set up a tent for me in the room. Just kidding. Anyway, one of the things I've been working on is a long experiment. I've started it back in November. It was for the idea of a really secure laptop. Today's world, it's pretty much, we've got all kinds of issues with privacy, and I'm sure you know, if you just take a hard drive out of someone's laptop, you can mount it into another computer and just look at all their files. Now, you've got things like full disk encryption and all that you can do, but so what I've been doing is going beyond just the norm with full disk encryption and just other things like that. I'm doing things like putting I'm putting the boot partition for the drive on a USB disk. This one in particular, because it has a number pad and it's encrypted pretty much by default. This is the Aegis Secure Key, the 8 GB version, which is their lowest capacity is about $100. I'm using this to boot up my laptop every time, and why? Well, here's why. Because unless someone has access to this and knows the PIN and all that fun jazz, they can't modify the boot partition. So no backdoors into the software, and why that's important is because you want to keep that stuff protected. There's a really good example, and that is Evil Maid. If you go to a hotel room, and let's say you're staying at the night, you leave your laptop there. Let's say there's a cleaning lady that goes in there. What they can do? Well, they can backdoor your laptop with their special piece of software to keylog and all that. That's all I've got right now in terms of I'm going to be doing I'm planning to hopefully do a bigger talk on my laptop project soon. I've got a lot of stuff planned, and hope to talk about it when I'm not speaking in front of everyone. So this was kind of impromptu, so thank you. Any questions about it? Anyone got any, yes?
What if you die? How are your loved ones going to get those cool pictures off your laptop?
It's a good question. Well, with this key, you can configure 2 pins. There's an administrative pin and a user pin. You can give them the user pin, for example, and then you can, and then with full disk encryption, the technology behind it is called Lux, which is pretty much you can add multiple passwords. So you can give them like a backup password, backup PIN, and they can unlock the drive. And then you can give them a user account too and give them a password for that, or you don't have to, but more than likely, that's all you would really need to set up something like that. Any other questions? All right, thank you.
Does anyone else have any side projects, side businesses, anything you want to talk about? Is there no one? All right, is J Gravity ready? Oh, awesome.
All right, so who likes text editors? Woo! Yeah. Who uses Vim? Woo! Who uses Emacs? Woo! Double woo for me. Emacs is really cool. You can leave it by pressing Control X and then Control C. That's all I have. I don't know. I don't use Vim. I restart the computer.
There was actually an article. There's actually an article. Stack Overflow had their millionth person look at how to exit Vim the other day. All right, is no one else wants to go? All right, is J Gravity set up? Almost. Stall. I can talk about my idea if someone wants to make sure I don't sit here and ramble for more than 5 minutes.
Who else has a project that they might want to, they're thinking about doing?
It can be a.
Or they think or they've done some work but aren't really, they think they might not be able to share it, but they get feedback for it.
I mean, you could have something you want to do, something you're motivated about.
Hey everybody, my name is Chris. I had an idea recently to basically open up the mailboxes that we have over at the dorms for everybody to be able to receive mail at the dorm. And then I thought, well, what if I could go a step further with that and have a way for everybody to be notified when they have mail in their mailbox? So I thought maybe I could set up something with Raspberry Pi and a few sensors in each box. And then just have a Slack bot that messages people. Yeah. Basically, I thought I would just use like an IR beam break to detect when there's mail inserted. And yeah, and the USPS should even like sort it all themselves, so that would be awesome. I would like take out, was it Ezekiel? Are you the one that usually sorts the mail if you're in here? No? Okay. Well, anyway. Oh yeah, that's right, yeah. So, yeah. Any questions?
That'd be really cool. What's the cost per sensor for that?
No idea. haven't put a cost to anything yet, it's just mostly in the concept phase, so.
You can find someone selling it just with itself. The Raspberry Pi is $5.
Yeah.
I can give you a Pi Zero.
Yeah, I can give you one too.
I actually am already using one that Tony lent me, so. But yeah, Joe?
What about packages?
Packages? Yeah, packages are a special case. I was thinking about maybe adding on to that later on. Have like an app or something that will scan for the name on the package. I don't know. Anything else? No? The mailroom? The front desk, where everything else is. So. Okay.
All right. Any more projects anyone wants to talk about? Do I need to stall more? Or are we good? Yeah, we're good. We're good? Awesome. Well, everyone, welcome to J Gravity.
Hi, everybody. So, I don't know if you all are aware of what we've been working on for the past, it's been, I think, 2 months, right, guys? Yeah, so basically, J-gravity is an n-body simulation designed to test the Janus model, which is this sort of fringe science physics model this guy has that explains dark matter as negative mass that repels positive mass, but also attracts negative mass. If you know normal physics, basically negative mass would also repel negative mass. So that's the difference between the Janus model and normal other models of physics. So we've got a PowerPoint for you guys prepared. Is there anyone? I am. Okay. I'm going to hand off to Phil.
What's up, everybody? I'm gonna come over this side, spread out a little bit. So we have this. Here's the presentation. So Sawyer covered a little bit of what J-gravity is a moment ago, but just to be a little bit more clear, this is a distributed computing project doing a large-scale physics simulation across many computers. We are trying to test some novel theories. We also can model totally standard gravity, which has been useful for testing because we know how that's supposed to work. We get to break a few 42 rules, like we're using a few outside libraries and stuff like that, but we were told to minimize that as much as possible. So the vast majority of it is in C that will eventually norm, and we only use a few libraries. And the main showpiece of the whole thing is that we're using the GPUs in the computers to do the processing. So a little bit about n-body simulation. Basically, you're going to break down the masses that you're trying to simulate into individual bodies. Usually those are stars, but say you wanted to simulate 1 trillion stars, you could have each point be the mass of 100 stars and it's just like they're close together and going to stay close together. We simplify the problem down to particles which have mass and position but no volume. And the gist of the problem obviously is that every single particle is exerting gravitational force on all the other particles, and computing that naively is O of n squared, and you want to simulate for a large number of particles, so it starts growing really, really fast. As you double the number of particles, it gets 4 times harder. And this is just a little bit more about the algorithm. Once we calculate the forces, then we can move them, and we do that for a discrete time step, and we do many, many time steps. So when we send the data out to the workers, and this is one of the core challenges of the project, it all has to come back to the server to update the data and redivide the work. So things are getting, there's a lot of traffic back and forth between the workers and the server. John, you want to talk about some of the challenges? You want me to keep going? I'll keep going. So there were a number of challenges in this project, and these aren't all listed here, but this is some of them. The first thing, as I was mentioning, is this is a hard problem. It's a lot of particles. It's a lot of math. Even when we got the simulation going very, very fast, like in tens of billions of particle pair comparisons per second, that still is a drop in the pond of how much work you have to do per tick, because for example, if you have 1 million particles, you have to do 1 trillion interactions because they all have to interact with each other. And as I mentioned earlier, I guess I got a little ahead of myself. The problem is state dependent per time step. All the data has to come back before we can start a new time step. And other challenges include storing the data that we produce. For example, for 4 million particles, each tick's data is something like 100 megabytes. And no, sorry, 66. And then if we were to do 1 billion, which we haven't quite gotten there yet, but those would be many gigabytes per tick. So storing it.
Like 14 or 15 gigabytes per frame or per time point for a 1 billion particle simulation.
Yeah, and for any of these simulations to be scientifically useful or even to draw meaningful conclusions from them, they have to be many, many time steps. So we're getting some extra storage, hopefully, for the big runs that we'll be doing later this week. Let's see. So because the problem is so massive, we do have to distribute it to the other computers. Also, that was like part of the assignment. So, but that adds substantial complexity. It does give you an edge, beating down the amount of work you have to do because you're spreading it around. But breaking up and distributing and returning and reintegrating all of the work is a substantial part of the challenge of the project. GPU programming is difficult. GPUs are, I mean, OpenCL is basically C, so it's fairly familiar, but there's all these restrictions and quirks that are not present on a CPU that are on a GPU. I get a little bit more into that on a future slide. It's difficult to gauge the accuracy, particularly when we're testing new physics models that we don't have a way to verify. exactly whether they're correct, but Sawyer helped us with that a lot. So.
If you're wondering how we tested everything, we'll talk about it later, but we have the GPU simulation is our main project, but we have another CPU-based one that I wrote and developed independently that we use to basically test everything. So we'll talk about our algorithm in a little bit, but before we ported that over the GPU, I wrote a CPU-based version of that, so where you could test it, and then we also use that version to test the accuracy of everything.
Yeah, essentially the idea was we discussed concepts and worked with each other on that, but in terms of writing actual lines of code, we worked completely independently, and then we're very pleased to find that our results differed by less than 1 part in a million. Yeah, yeah, okay, yeah, like 1,000th of a percent or something like that. So clearly, hopefully, we're either both wrong or we're both right. I'm hoping it's the one way. And then the last challenge is interacting with the system. You know, good debug output, good visualizing, the web interface, all of these things which are equally vital in turning this into a functional tool, not just a neat thing that we hacked together. So the goal is a web interface where a scientist or an interested party could say, I want to simulate mass that's distributed like this, there's this many stars for this much time, and then the cluster would take that and run it and eventually return the result of it. Okay, so this is sort of my department, so I guess I'll keep the mic. Tackling the computational load. I've covered a little bit of this before, but here's some more specific numbers. The very first implementation was a brute force where every particle is comparing with every particle on the CPU. It ran very smooth up to 4,000 particles, and we could push it up to about 8,000 particles before it started really chugging. We moved that similar brute force algorithm over to the GPU, and we were able to get up to about 100,000 particles, rendering at 20 to 30 frames per second, but anything beyond that started to really chug as well. So that's where we started moving into the distributed approach. And, well, actually, before the distributed approach, there's another key way that we reduce the workload, and it's this thing called the Barnes-Hut algorithm. Essentially, you divide space into equal octants. A binary tree divides a line into halves and then quarters and then eighths. This is like that in 3 dimensions. So you take a cube and you divide it into the 8 cubes that each make an eighth of that, and then you can subdivide those further. And essentially, you get this hierarchical tree where things that are near each other spatially are near each other in the tree. And you can use that. There's a simple tool that I think I go in a little bit more depth later, but basically it gives us this nice convenient function where for a cell in the tree, I can compare against another cell in the tree and know whether that one's far enough away to approximate all the particles in that cell as just one cell. You can think about it like, we're in the Milky Way, and there's the Andromeda Galaxy fairly nearby, and every individual star in the Andromeda Galaxy is individually exerting force on the Earth right now, but they're so far away that we can just treat it as a single mass that's the total mass of all of those stars that far away, and the math is, it's a part per trillion or something difference. So essentially this relies on that. Things that are far enough away, you can treat them as a single body. And it reduces the workload massively. You still do have to do brute force comparison of the things that you do have to do near individual comparisons with, but those sets are much smaller. So it's still n squared, but n gets a lot smaller. And you can build that tree very fast. And it conveniently results in blocks of work that are completely functionally independent from each other, and those are what we distribute. There's the slide that goes with everything I just said. Right, so GPU, and I'm going to be handing off after this slide, I promise. So we used OpenCL, because OpenCL is what runs on the AMD graphics cards that are in the lab computers. The other competitor for OpenCL is CUDA, although functionally languages are basically identical. GPUs are awesome because they can calculate massively parallel, just on hundreds or thousands of, if it's doing the same operation, it can do it a couple hundred to 1,000 times, on each member of the set in parallel. But there's problems of the functions have to execute very predictably. So you can't have anything really conditional. You can't have things that are branching. You can't have things that are recursing. So you basically have to design a function that's going to do the same thing for each element in the set, and then you can unleash it on a giant set, and it goes insanely fast. So this, it's been really interesting and really challenging working on this. Tuning it is weird. You can do things that way fewer lines of code, seems like fewer operations, and it makes no difference or even goes slower. And then really strange things that you can tweak, like the type of a variable, or whether something is an argument, or versus whether something, say, changes a pointer versus returning it. That can increase the performance that you get by 10, 20%. And it's been an interesting world to try to navigate. But once the code gets good, the GPU is such an incredibly powerful tool. I'm definitely going to try to use it on almost anything I can use it on in the future. And as I mentioned, yeah, we got up to 44 billion particle pair comparisons per second, which is a pretty good result, I think. We're getting it's about a teraflop, if that term means anything. So trillion floating point operations per second. So distributing the work. This is not my department.
Okay. So basically, I'm just going to walk through how the solution is arrived, or how we create the various different frames from the original. So first, we have our initial data set, which is all of, like, for example, a initial set of points and velocities and masses for those points. Spread out evenly. I think in our tests we have it's done in a sphere. Yeah. And basically, once we get that to our dispatcher, so basically we have one dispatcher, which is basically our server, and we have n number of workers, which are the max that we're using to do all the computation. And basically, we take the initial data set onto the dispatcher, and then using the Barnes-Hut algorithm and octrees, we divide it up into work units, which are independent of each other and can be completed at the same time. And then we go through and send out all those work units to the various different worker computers, at which point they do their computation and then package their results, and then they all send it back to the dispatcher. And once that happens, you have all the data on the dispatcher. It's merged into the next time point, essentially. We call them ticks. So ticks or frames, you can think of it that way as well. And then this process basically repeats for however many frames we want to compute. So in terms of communication to all the workers, we decided to go with TCP because it does have some redundancy and protection for sending data and making sure it arrives at its destination in order and make sure it doesn't get disformed. And we also have a lot of multi-threading that we did on the dispatcher. So we're spinning up one thread solely for connecting workers, and then one thread for communicating with each worker. And I think that's about it. Is there anything else?
No, I think that covers it. Yeah, the using TCP because we needed to be sure that the data stayed integral is definitely an important point, because as we're saying, data comes in, that becomes the data set for the next tick. So if there's any transmission errors, obviously the entire thing could be ruined. So we got the impression that maybe using UDP we might be able to get better network throughput, but we decided not to do that, again, for certainty of not having errors. Verifying our results. Sawyer, that's you.
All right, I already talked a little bit about this, but to get more into it, essentially, Phil already described what the Barnes-Hut algorithm does. So it's a great algorithm. It massively, massively reduces the number of comparisons that need to be done, but obviously there is some accuracy loss in that. And also in the GPU code, we have to use floats for speed reasons, so there's a little bit of accuracy loss of the floating point stuff. And then there's a whole lot of other little areas where the accuracy can be lost. So my job was to basically design a set of simulations that could be run that account for all those accuracy losses by either getting rid of them or accounting for them. So there's not really much more to talk about it. but it is really, really close in accuracy, like less than 1%. The differences are minuscule compared to the size of the simulations we have.
Yeah, so
I forgot, because I literally did this last night, but we just added special relativity, if anyone thinks that's cool.
yeah, so the need for this independent verification system kind of emerged as the project went on. We started by simulating known systems, like the very, very first J-gravity thing was the International Space Station orbiting the Earth. Then we did the Earth orbiting the Sun. Basically, the idea is, you can look up how fast the Earth is moving around the sun. If you make a particle the mass of the Earth move that fast around the mass of the sun, does it orbit? Then you have a decent idea that what you're doing is at least similar to the truth. But as the particle count grows and as we mess with the physics, we really need a computer verification system because you can't just look at it and tell if it's working right anymore. So bottlenecks, which we've had something like a working product for at least a week now, if not getting closer to 2, but it has been nowhere near the performance level that we think we can attain. So we've been primarily fighting down these bottlenecks. The individual workers can churn through the work lightning fast. We've actually been having a really hard time keeping them fed. We refer to them as being hungry, and you have to keep them fed. It's tricky because a gigabit per second actually starts being a bit of a restriction once you're talking about moving around many gigabytes per tick. So we've come up with a couple of approaches to beat that. The first one was adding some fast compression, and I alluded to earlier, we are using a couple outside libraries. This is one. We're using LZ4, which is sort of an industry standard for fast compression. The ratios are not amazing, like we get down to 85%, but it's like only twice as slow as memcopy or something like that, so it's pretty great. It's basically just free extra bandwidth. We use this thing called turbo transpose to enhance the results of LZ4. It basically shuffles the bits around in a way that compresses better and then shuffles them back at the end. We improved the distribution system. This is what John has been working on a lot lately, to always be set to maximize. If we are being held back by the width of our network pipe, we need to at least make sure that we are using it 100% all the time. So more multi-threading, sending to more workers at once, trying to keep the network saturated. And then lastly, this is not yet implemented, but it's probably going to be the last major thing that we do put in the code. It turns out that these work units that we're sending out independently have massive overlap with each other. Like, we talk about them as neighborhoods, as in, like, when I'm computing for these stars that are here in space, I need the stars that are, like, around it. So then these stars that are right to its left, their stars that are around them, there's a lot of overlap between those two. And we found a clever way to kind of roll those all together. And we're getting down to like 10% of original transmit size. We just haven't fully implemented it, but the early results are looking good. Visualization.
Pablo's not here, but he's our visualization guy. He will be back for 2 days before we present this fully. But he was using C++ and the STL2 library to take our entirely ginormous data set that we generate and visualize it. It looks pretty cool. If anybody wants to see it, I do have it working on my computer in the Bocal. Please come by and check it out. We're going to show it to Cool, sorry. I was at IKEA buying furniture for the school. Challenges, yeah, nice, somebody updated these. But yeah, trying to get this out to a file is tricky. The format that we can do it in is gonna either take a long time or it's gonna end up being ginormous. Loading it into RAM, if you don't, if you load this into memory, it's so huge that you're gonna end up, you need to really read it out of the file, because if you load it into RAM, you're doing double the work, and since there's such a big amount of information, doubling your work is not what you want to do. And integration with other parts of the project, that's been difficult just because we've had it working for like almost 2 weeks now, but how do you, the visualization is like the end of the chain, and it needs to be then brought right back to the front of whoever typed in the data sets needs to see what's happening. Web interface, the web team and I have been managing getting the information out to people that are interested, so just like the public-facing side. But more importantly, we want to allow anybody that is interested, that has their own data sets or their own hypotheses, even like checking the space station or doing that and testing accuracy, they'll be able to put in their own data sets and run them. An issue that comes with that is that we have to make sure that it's not just anybody that can put those data sets in, but at the same time we want to allow anybody. So we need an approval system, and that requires a back-end authorization and all of those steps. We actually have that approval, and we're using Django for the back-end process and for the forms and everything, and we have the database running. But the issue with that is I've hit a snag moving it into production, but that can be resolved in the time that we have. Then it needs to communicate with the dispatcher. Once the production database is up, that will be the primary concern, because until it's in the production database, asking the dispatcher to go to it while another user comes to it, we'll have concurrency problems, and the database will die, and we'll lose all the data sets that we already asked people to have. That pretty much covers those challenges. And goals before deadline.
Thank you. I think we actually kind of covered some of this already, but yeah, so we've got a last few couple features to implement. Then the plan is to basically freeze the code in a couple days, only bug fixes, no more features, and just be testing aggressively. There's a few more bugs, maybe a couple memory leaks, although I think we're good on that front. And there's still a bunch of performance tuning to do, like we don't know, because of the whole network saturation issue, it might be better to have fewer computers per row running it on more rows, because the big server can talk to each row independently. You know, we got to figure out what the best numbers are, and then as soon as we have good data for that, do some really big runs. That's the one area that we haven't really stress tested yet. We've done long runs on small sets, and we've done short runs on large sets, but we need to do a long run on a long set, because that is the end goal. And also, we just got word today, confirmation, it's been a bit iffy, but we are going to get some really sweet hardware from AMD. They're sending us a desktop box with a CPU that's not even out yet, and some 4 GPUs. And we're going to have that. It's actually probably going to take care of it's going to do about 60% of the total simulation work, I think, because it's going to be able to outpace the Macs upstairs so much. But that's going to be really fun to play with, and I really hope we have enough time before the deadline to really get it going. Web interface is coming along great, but is still coalescing. And like Mason said, the interaction between all these separate parts of the project. And then our hope is to also write a more formal paper and do a technical presentation that we will be doing at the job fair on the 16th. And we're also probably going to be doing another MoonLight presentation next week to show the updated version of this presentation with more visuals and more data. But I think that's the last slide, right? Yes, cool. So that's the presentation. I'm going to get the small amount of data that we do have to show ready to show, if you want to take questions, I guess.
Yeah, I'll take questions. Yep. So, guys, any questions?
We can take him. Come on, you guys.
Early on, we did a lot of design, so we had a general idea. Like, yeah, the answer is basically mostly yes. We did have a general idea at the beginning when, once we completed our designing, how we wanted the whole thing to work, and then basically we, just fleshed out the design more, and then got coding. Does that answer your question?
There was actually one point earlier. We talked about the algorithm we're using, Barnes Hut. We played around with another algorithm called Fast Multiple Method, or FMM. I actually have a working demo of that on the GitHub, I think. But basically, we ended up going with Barnes Hut because of its simplicity compared to FMM. While FMM is faster, our network, at the time, we were concerned about increasing the complexity of how the networking aspect worked with it. And I think that was a good choice in the long run.
Yeah, I was more talking about like the high-level design. Like, yes, we changed a lot of the algorithms and like how we approached some like dividing up the work and stuff. But like, for example, what was there from the start was the whole, divide up the data set and then send it out to the workers, have them compute it, and then bring it back to the dispatcher to divide it up again and repeat that process. we basically had that process at the end of our design. Any more questions? Yes. What's so good about this particular compression is it's really fast. So like it takes very little time to compute to actually do the compression and decompression. That's one of the reasons we went with it. There are some more, and also like we had to take into account like the types of data we are compressing. In our case, I think we're compressing floats. So this particular algorithm is really good at compressing arrays of floats. Does that answer your question? Or yeah. Phil, do you wanna?
So actually, just to clarify, we were looking into a compression algorithm that's very well suited to floats. There's this thing called ZFP. It's amazing, but your floats have to have certain mathematical properties that ours do not. So what we ended up doing actually was using LZ4, which is strict, just compresses any binary data. It's kind of like, it's like zip or something, you know, it just looks for recurring patterns in the bits and compresses those in a very sort of traditional way. It's just lightning fast. We hoped to use ZFP because it gets compression ratios of like 2 to 3% original file size, but the floats have to be three-dimensional samples from a continuous field, which is common in a lot of scientific fields, but not this one, so we couldn't use it, unfortunately. Unfortunately, also, we are having some slight technical difficulties with running the visualizer on the computer that this is hooked up to. It doesn't have SDL installed or something. So we are happy to show the visualizer to anyone who wants to come find us in the lab after the presentation, but unfortunately we can't do it up here. But I think we are going to show the website, yeah? Is that the plan? Yeah. Okay, cool. All right, any other questions? Oh, that's a really good question. So our hope when we do the big runs is that we're going to use actual real-world data, but for now we've been randomly generating sets with sort of normal distributions. We originally started with randomly placing spots in a cube because that's really easy to do, and we've moved to random distribution on a sphere, and you know we have some variables that we can control to make the sphere perfectly round, a little bit depressed, you know, different properties for the velocities. We have some sets we've run where all the particles start still, start with small random velocities, or start orbiting the center. Those are the ones that have come up with the coolest visuals and that look the most sort of galaxy-ish. But yeah, we're basically, the straight answer is that we're currently basically making up the data, but we will be using real-world data for the large sims. Anything else? Sure. Yeah, that's a really good question. We were actually discussing right before the presentation the fact that we did not include that in the slideshow, despite the fact that that was a huge part of the project. I don't think any of us have experience working with this large of a team before. It was definitely, it's been great. It's also been very challenging. The process was that we divided up into teams based on interest, and we had some macro discussions about how those departments would interact, and then those departments designed their internal workings separately. We kept talking. The design phase was, there was no distinct end to it, but it went on for the first couple weeks, and then we moved more into each department doing their own thing. We all, I think, leveled up big time on our usage of Git, actually working a many-person project with lots of merges and commits and branches and all that. I certainly went from basically knowing nothing about advanced Git stuff to having a decent handle on it now. And yeah, organizing a large group of people has definitely been a challenge. I know that at various points in time, there have been substantial miscommunications between teams. There have been people who feel like they don't know what they need to be doing. And we were all learning as we went. I think we've gotten better towards the end, but yeah, so it's been a learning experience, I guess would be my answer to that. We were actually literally having this conversation right before coming down here, and we are still coming to that conclusion. It was a difficult project to organize in a structured manner because we had to do so much so fast, right? We all had to learn a bunch of new stuff. We all had to be working on a bunch of different things, and if we didn't get started pretty quickly, we were not going to hit the deadline. So I think some people, myself definitely included, I definitely like rushed into prototyping my branches very quickly before the planning phase had really committed and completed. So I think what we would do differently would be plan more firmly and rigorously, but also maybe quicker. Actually, I think what would have been really beneficial would be a multiple iteration system. Let's do broad design, write some code, see how that influences our perception of how the more detailed design should go, write some code. But
do a little bit of that with like all of our optimizations. We came up with an idea of what we felt was best. Then we coded it out, and then we went to improve it.
definitely. Website time?
So this is like I was talking about. I'm in the middle of like moving this to production, and so we have the static pages here to show you. Next week we'll have the actual web application, but this is the public-facing site, and the thing that it's going to be lacking that I really wanted to show is the form that you fill out to populate the data sets in the back end where you can approve that. So imagine that if you will. But here's our landing page. We're simulating the Janus gravitational model. We're giving credit to the model that was that we're basing this all off of, but also we want to go through and explain what in-body simulations are, and we have a nice, awesome little effect for that wow factor that you want as a user when you go to a website. If you just like, woo. We went through and looked at different templates and things to try and figure out what kind of site we wanted, and we kind of decided we want something that looks really really good for someone that even doesn't have the technical side. But then if they have the technical side, we want to let them contribute and add to the project. And so that's what the web form will be. We have a few more pages. A lot of these were actually redesigned from our mock-ups just recently even. But page? I don't have a clicker or a mouse, but we have a few other pages. But anyway, click. Not. We're also moving from what was a single-page website 2 days ago to a multi-page website, and so you've got to click the navigation up. Click the buttons you clicked earlier, please. Anyway, there's a beautiful-looking team page. There's a nice team page that they might show.
There we go.
Also, this goes through and explains the teams. We did this in the presentation, so I really wanted to show the person page so we can take a bow. Our team. Click right there, guys. I know. All right, but anyway, this part's pretty silly anyway because this will be up in production probably by tomorrow night or Friday night, so that anybody in the school can just go to it live, and then we'll have it also live to like the internet as well. It'll be on jgravity-host inside of the lab, and then I'm going to be purchasing a domain name for it as well, so it'll be something like j-gravity.com. Oh, all right. That's going live for you. All right. Thank you for coming to MoonLight, and I don't know if we're the last people presenting, so yeah. All right. See you next week.